everyone, welcome to discussion 11 for CS61B. Today we're going to be talking about graphs and MSTs. So first things first, let's get some announcements out of the way. There aren't that many right now. So the first thing is that Project 2C is going to be due next week. And the second thing is that the election is happening this week. We want to relieve as much stress as possible, so there's nothing due this week. There's no discussions, no labs. Hopefully you guys have some space to breathe. If you find yourself struggling with all that's going on with the fires and the power outages and all this, and you've run out of slip days, please reach out to us. We promise we will do our best to work with you and figure out a solution. So with that out of the way, let's get into some content review. So the first thing that we're going to talk about is minimum spanning trees. And so what is a minimum spanning tree? Well, a minimum spanning tree is a subset of a graph. It's a tree within a graph that connects all the nodes in the graph while being as light as possible. So the sum of the weights of all the edges is as small as possible. So if you look at this example over here, you see that there's no way to connect these all the nodes in this graph better or with less weight than what we're doing right now. Like if instead of having this line over here, I did like this line over here, we're adding 7 instead of 1, so that's not a minimum spanning tree anymore. It's just a spanning tree. And so MSTs aren't always even unique. It's possible to have multiple MSTs that have the same weight. So an example of that here would be, we don't necessarily have to have AF be connected like this. We can have AC be connected like here. Because both of these are 2, they're both equally light, and so they're both minimum spanning trees for this graph. Moving on to Prim's algorithm. So this is one of 2 ways we're going to find MSTs, and we're going to talk about it in a very conceptual way, very over the idea part. We're not going to probably ask you to program this at any time. It might come up as a test question, but it's not part of this class to really go into the nitty-gritty of how it's programmed. And so the way Prim's algorithm works is you start with the nodes. Let's say we start with A. And so from this node, we find, okay, what is the smallest edge leaving this node? And so we see 1, 2, 3, and 7. And obviously you see that 1 is the lightest. So we're going to go here, and we're going to also include C in our MST. So now we're going to look at all of the edges leaving the MST that we've created so far. So we're going to look at the edge that is of weight 7, of 3, of 2, and of 2. So we're looking at edges that are connected to C and to A in this case. And so we're trying to find the smallest edge that leads to a node that's not already in the MST. We have 2 options like we had before. I'm just going to pick the top one, but again, both of the options lead to valid MSTs. So we're going to add F now. And now we're going to consider even more, right? So now we're going to be like, okay, what are all the edges leading our MST? So we have this, we have this 1 right here. We have this 3, we have this 7, and we have this 2. So the first thing we realize is, oh wait, we can't have the edge that's of length 2 because it's going to lead to F, and F is already in our MST. And so this will create a cycle, which we don't want. Remember, trees don't have cycles. And so instead, we're going to consider the other 3, and obviously 1 is the smallest, so it goes like this. And then we just keep going in that pattern until we've added every single node in the graph to our MST, and then we know we're done. This is one way of finding an MST for a graph. The second way is called Kruskal's algorithm. Both of these are named after people. So the way Kruskal's works is that instead of starting with one edge and kind of like spreading through the graph like we do with Prim's, we go through the entire graph in order, adding the lightest edge that doesn't create a loop at each time step. So the first thing we'll do is we'll look through all of the edges in our entire graph, and we're like, what is the smallest edge? Well, we have 4 options. We can pick any of them. So I'll just pick this one that's like BD. And then again, next time we'll do it again. And the first 4 edges are kind of obvious because they're all ones, and none of them create graphs. Oh, none of them create cycles. And so we'll keep going. And now we can look at these three, right? All these twos. Well, this two can't be it because this, connecting this would create a cycle where B, E, and D are in a cycle together. And so that's automatically out of the running. So we have two options now. You can pick either of them. I'll just pick this one for now, I guess. And so now we consider the last edge and we're like, oh, wait, we already have one here. If we add this as well, we're going to create a cycle. So what we're going to do is we're also going to say that this is not an option and we're going to move on to the next highest. And at this point, we actually can take a look around and realize that we've already finished our MST. So there's no need to keep going. But basically, you keep going until you have enough edges to span the whole tree. Same as prims. They act very similarly. They don't always return the same answer, however. Both cruscals and prims will always return an MST of the same size, but they may not return the same MST. Like in this case, prim's algorithm returned this one, which has like this line in it, and cruscals returned one that has this line. And that's purely implementational. It purely depends on just which order you're traversing the edges in, / the nodes in. And so that's definitely something to consider, but if there is a unique MST, prim and cruscals will return the same thing. Otherwise, he'll definitely return something of the same weight, but it may not be the same exact MST. Okay, last thing today. Today's kind of just one of those days where we're covering all the small things that we haven't had a chance to cover yet, is topological sorts. And so topological sorts involve taking a graph with no cycles, so a tree basically, and laying it so that all edges point in the same direction. So an example that's very common that I love bringing up is like the prerequisite graph for the computer science classes at Berkeley. If you look at HKN, they have a big graph that has all the possible CS and EE classes that you can take at Berkeley, and they kind of they have all lines pointing to what's a prerequisite for what, is it required, is it just recommended? Anyway, so simplifying that a little bit, we can kind of start with this graph, right? We have 61A. You need 61A to take 61B. In my opinion, you don't super need 61B to take 61C. They kind of cover different things. But you definitely need 61B to cover 186 and 170 because you need the coding part to do 186 and you need the graphs part to do 170. And you also need some 70 to do 170, but you don't need anything else to take 70. So with that, we want to basically align the points in this in such a way that all of the lines point to the right. And so what that ends up being is we have 61A because it has no prerequisites. 70 also has no prerequisites, so we can kind of put it anywhere. Like the example, the final answer I have down here has it over here, but 70 can go literally anywhere because nothing leads to 70. Nothing has to be before 70. So we have 61A and 70 with no prerequisites. We have 61B with 61A as a prerequisite, and also 61C with 61A as a prerequisite. And then we have 186, which has both 61 or just 61B as a prerequisite. And then you have 170, which has both 61B and 70 as a prerequisite. So basically, topological sorts are also not necessarily unique. All they require is that all lines point to the right. And so this is one possibility, this is another possibility. There's tons more with this specific graph. You can move 70 over here, you can move 70 over there. You can move 70 anywhere as long as it's before 170. You can move 186 anywhere as long as it's after 61B. Lots of options. But yeah, a topological sort just basically means take the graph and put all the nodes in an ordering such that all of the lines move to the right. Okay, let's move on to the worksheet. So the first problem is on minimum spanning trees. And so the first thing we're going to do is try to perform Prim's algorithm on the MST starting with A, and then we're going to see what we get. And so if you ever come across a tie, you're going to go with the letter that comes alphabetically first. You're going to break the tie by picking the letter that comes alphabetically first. And I will give you guys a couple minutes to think about it. Okay, welcome back. So let's figure out how Prim's algorithm would do this. So the first thing we're going to do, we're starting with A. So we can kind of just mark A as in our MST already. And so now what we're going to do is we are going to figure out which one of the edges going out from A have the lowest weight. And so we have 2 and we have 1. And so we can kind of see that 1 is obviously the smaller edge, so we're going to pick that one. And so now we've added C to our MST. Now we can look at all the edges coming out of both A and C. So we have, oops, that's not what I meant to do. We have both this 2, this 2, this 2, and this 3. And so obviously any one of the 2s would be a good choice, but we'll pick the one that comes alphabetically first. So we will pick this one because AB. And then we will reevaluate with B in our MST, looking at all edges leaving A, C, or B. So now we have this 2 again, 1, 2, 3. And so obviously the first thing we can say is, oh, this won't work because obviously it's connecting B and C, and that's going to create a cycle. So we can see that the lightest edge remaining is going to be going from B to D. So we can just add that directly to our MST. And then we get this MST for now. Again, repeating the process like I said before, we get 3, 2, 2, 3, 4. We can immediately cross out anything that would cause a cycle, which means our new lightest connection goes from C to E, because alphabetically that comes first. Bam. Now we're going to reset one last time to get this last node, and we can figure out everything leaving our current MST, crossed out everything that may create a cycle, and then we're left with 2 options, one of which is clearly better, so we can just pick EF. And this is the MST for this graph. So we have the Prim's version, and now we're going to do the same thing but with Kruskal's algorithm. And same rules. I'll give you guys a second to think about it, and then we will reconvene. Okay, welcome back. Let's talk about it. So remember, while Prim started at a specific node, Kruskal's just picks the smallest lines from the graph. And so the first round, we see that there's three lines that are all of weight 1. None of them are going to create a cycle. So we can add all of them immediately. So we got this, we got this, and we got this. And now we go into round 2. We look for the next round of smallest edges. So we get this one, and this one. And we can only pick one of these because picking any more will create a cycle. So we pick the one that is alphabetically the smallest, which is in this case AB. And now we can't pick the other 2. So we can just cross them off our options list and move on. So now we can pick the next highest, and we are left with 2 options. Again, both of them work, but either of them would work, but if we did both, then we would get a cycle. So we'll pick the one that is alphabetically smaller, giving us CE. And so now we have finished our MST. All of our nodes are connected in one group, so we don't have to keep going. In this case, for this problem, the Prim's algorithm and Kruskal's gave the same MST, but again, not always the case. We just got lucky. Moving on to number 2, we're going to talk about topological sorts. So the first problem is, what is a valid topological sort of this graph? I'll give you guys a minute to think about it. Okay, so in finding a topological sort, there's two main approaches that both work. One is more general case and one is quicker. And so the more general case one is that if you take the depth first search post order of any graph and then you reverse it, you will automatically get the valid topological sort. So we can try that first. The second approach is an intuitive approach where you just kind of, if a graph is relatively simple, if you think you know the answer, intuitively you can just kind of be like, okay, well, so we put A at the beginning, then we kind of go to these two, and then I guess D has to go before B's, and you can just kind of work that out yourself. But the more general case, the one that always works, is doing the depth first search post order and then taking its reverse. So as a quick reminder, let's just do the depth first search post order. So we're starting with A, right? So we go to A, but we have not visited A yet. So we're at A. Now we're going to go to the thing that's lexigraphically, is that the word it is? Next. And so we have B. And so again, we're doing a depth first search. So we want, and post order. So we want to visit all of an item's children before we visit itself. So we are again at B, but we're not visiting B quite yet. We're going to go to the B's child, which is C. And then we're going to go down more. And finally at F, we hit a point where there are no more children. So at F, we can finally visit F. And then we can say F is the first item in our post order. And now that we visited F, we can go back up one. C has no more living children. So then we can visit C. Go back up one. B has no more living children, so we can visit B. And fortunately, A does have more living children. So now we got to visit D. So the first thing we look at is B, but we realize it's already been visited, so we automatically go back. Next, we go to E. And we go to E, but again, we don't print E yet. So we go from E to F, but F has already been visited. So we go back and we visit E. And now that we've done that, we can go back up to D. And finally, we can visit D. And then, because obviously F, I didn't mention that, but we've already visited F. And then we can go back up one and visit A, finally. And now we're done with this subset of the graph, but we do have this lonely G, so because we haven't visited it, we'll go there. Its child has already been seen, so we go back, visit G, and add it. This is our DFS post order. And a valid topological sort of this graph would be the reverse of that. So topological sort would be G, A, D, E, B, C, F. It's not the only topological sort that's valid, but it is one that works, and it always works for every graph, as long as there are any cycles. So in this case, if we want to kind of draw out what the actual topological mapping would look like, we have G, we have A, and both of these have nothing pointing into them. They could be interchangeable. We have D, which has A pointing to it, so I'll add that arrow right there. We have E, which has D pointing to it. We have B, which has both D and A pointing to it. We have C, which has F pointing to, or C, which has B pointing to it. And then lastly, we have F, which has a whole host of things pointing to it. It has C, it has D, it has E. I guess I should have done E first. That'd be at the inside. E, D, and G, all pointing to it. And so as you can see in this sort drawn out, all of the lines are ultimately pointing to the right, which makes it a valid topological sort. You can also see that we can easily switch the positions of G and A, and it'd be completely valid. We can switch the positions of E and B, and they'd be completely valid. So there are variations on this. This is just the easiest one to get and has like a more straightforward methodology. Okay, so I guess I don't have my slides for the other parts, so we can just talk about it. So, next question for part B is, there are two requirements that a graph must satisfy in order for there to be a valid topological sort of the graph. What are they? I've kind of mentioned these already, but I'll give you guys a second to think about it, and then we will talk about the answer. Okay, welcome back. So the first thing is that the graph must be directed. So what that means is that like all of these lines should obviously point in some direction, because it doesn't really make sense to do a topological graph if the graph is undirected, because things aren't really like prerequisites, or like nothing comes before anything else in an undirected graph, right? Like both things are basically pointing at each other, which is kind of, you can visualize that as a cycle, which is the second point. The second rule is that there can't be cycles in the graph. And so if there's any sort of cycle, you wouldn't know which node should be first in the topological graph, because no matter what you did, you would need something to point backwards. So graphs that satisfy both of these are called directed acyclic graphs, or DAGs. If you go on to take 170 after this, you'll hear a lot more about those, but this class doesn't really go into it. So all you have to know are these two rules. And then part C is, why does using a reverse post-order DFS to compute the topological sort even work at all? I'll give you guys a second to consider it, and then I'll tell you the answer. Okay, welcome back. And so basically, if you are in a situation where DFS can be called, which is on any graph, there are basically three possible cases that can happen, right? And so let's say you have an edge UV, and what happens when you call DFS on that edge? So the first case is if you've already called DFS V before, and remember, this is post order, right? And so you will have already visited U, and now you're visiting V. So that's fine. The second case is DFS-V has called in the past, but it hasn't finished visiting V. And that means that there is a path from V to U, and now there is an edge from U to V, which means it's not acyclic, right? And so therefore this is impossible, because what happens if you've already seen V but you haven't returned means you're in a situation where you've been to V without visiting it. You go to some other vertex, U, maybe you go somewhere else, and then somehow you're getting back to V without having had visited it already. And if that happens, that means clearly you have a cycle in your graph. So it's not possible. And then the last option is if you come across V, the node, and you haven't called DFS on it at all ever. And so in this case, it'll eventually degenerate into one of the previous cases, because once you call DFS, either you go visit U, my pen went away. Either you go visit U, go back, visit V, everything's all peachy next time you come, it's already visited, or you go visit U and somehow you end up coming back to V without it being visited, and it's a cyclic graph. And so basically you can try it out yourself. This is just one of those things where it's kind of hard to prove to yourself that it's true. So if you want, you can just draw out some graphs, try depth first search, and see what happens. But in general, you will always end up with a valid topological sort if you reverse the post-order DFS of a graph. Ooh, I skipped 2 slides. Okay. Going back to graph algorithm design is more conceptual level. Let's do some problems on that. So the first problem is an undirected graph is said to be bipartite if all of its vertices can be divided into 2 disjoint sets. So what that means is a graph can be bipartite, or it's basically made up of two like teams, let's say, where each node is only connected to members of the opposite team. So an example of a bipartite graph may be like if you're in a situation like this, and things are only ever going across. And so this might be like team A and this might be team B. I don't know why I did it backwards. But like there is no member of team A connected to another team member of team A. So we can like color these in, right? And so the idea is that this is what a bipartite graph is. And so they're saying that if you have an undirected graph where all of the vertices can be divided into two disjoint sets, such that every edge connects an item in U to an item in V, provide an algorithm that determines whether or not a graph is bipartite. And I'll give you guys a bit to think about it. And please think about this because it's kind of an interesting problem. Okay, welcome back. So the first thing I'm going to do is kind of just draw out the case that's written in the worksheet. I didn't have this on my thing from before. So we have V up here and U down here. Okay, so this is the example we have, right? And so there's two options of ways we can approach this. We can approach this either with a depth first search traversal or a breadth first search traversal. And so the biggest thing in this is if you ever, in either traversal, if you ever come across a point in your traversal where you've just left an edge that was marked as V, and you stumble across an edge that has already also been marked as V, then you know you have a problem. So an example would be, let's say you have this, right? You have a very simple cycle, right? So let's say you come to view, right? And you're like, okay, let's do maybe a depth first search. So you start at U, you do a depth first search. So you mark this as U, you mark this as V, and now you're going to keep going, you're going to mark this as U, and you're like, okay, well, at this point, I go back and I realize, oh no, I am next to a vertex that is also U. And in that case, that's not great, right? That means that we have some sort of situation where it is not possible for it to be bipartite. And so we immediately know. And if the graph isn't connected, if there's like separate distinct parts, you just repeat this process for everything. And it will always let you know if you have a situation where it's impossible for the graph to be bipartite. And so the runtime of this algorithm is the same as it is for breadth first search and depth first search, just E plus V. Then I'm sure there's also, by the way, plenty of other ways to do this. But yeah, that's just one solution on how to determine this. The next thing is consider an implementation. Look at the worksheet. I don't have the implementation on my slides of DFS, which contains a crucial error. And give an example of a graph where this algorithm may not traverse in DFS order. And I'll give you guys a minute to think about it. Okay, welcome back. So let's take a look at this implementation. So the first thing we have is a lovely stack, right? And so let's say we have a situation where it's something like this, first of all. A, B, C, and D. And they're all children of A, right? So we have a stack. So we pop A in, and we already mark it when we pop it in. We pop A out, and we're going to add all of its children. So we add D, C, and B, and we mark them all as we pop them out. And this is a fine traversal. This is depth first search so far. But I want you to consider the case where what if B was also connected to D? Well, in that case, D has already been marked at this point, right? Because C and D were marked when they were put into the stack. And so since D is already marked, we're not going to traverse it immediately. So our order is going to be A, B, and then whatever is next in the stack, which is currently C, and then D. So even though a traditional depth first search traversal would go down, down, and then up, up, down, Instead, we're doing more of a breadth first search. We're finding all the children that are equally far away from A first. And so this is a case where it doesn't do a depth first traversal of this graph. But there are others, and I hope you found one. Okay, last problem. So this one's an extra problem. Provide an algorithm that finds the shortest cycle in terms of the number of edges used in a directed graph in O of EV time and O of E space, assuming that the number of edges is greater than the number of vertices. I'll give you guys a second to think about it. Okay, welcome back. So remember, one thing to keep in mind is that when we say shortest cycle in this question, we mean in terms of number of edges used. You can also think of it as every edge is just of weight 1. So, what can we do? Well, what we can think about is, the shortest cycle goes from an edge to itself, right? So that means that we can just look at each edge in the graph and figure out what is the shortest path from that edge to itself, and whichever one of those nodes has that shortest path has the shortest cycle as well. So for each node in the graph, what we can do is start at that node, and then we can use breadth first search because we're defining shortest cycle in terms of the number of edges and not the weight of the edges. And breadth first search just goes like one by one. So we'll just keep going breadth first search down, down, down until we get to a point where we somehow get back to our node. And since we're going by breadth first search, we'll look at all the nodes that are 1 away, all the nodes that are 2 away, and on until we find ourselves again. And then however far this path is going to be the distance from this node to itself. And in the worst possible case, you're just going to check every edge in the graph, right? To figure out the shortest path to this node, because there just isn't going to be one. And so the worst case for each checking the shortest cycle for each node is going to be O of E. And so if we do it for every single vertex, we're going to get O of E V. I mean, the subroutine, technically takes O of E plus V time, but because E is greater than V, we kind of just got rid of it. So don't get confused about that. But yeah, that's it. It's just breadth first search from each node until you find itself again, and then you take the minimum of all of those options. Well, that about wraps up our discussion for today. I hope you guys have a good week, and I hope you are all staying safe at this time. Good luck with the rest of your week. Bye.